Lab 5 Objective 1, 25% brightness. In this objective, we use the pulse width modulation feature of the Arduino board to control the intensity of light emitted from the LED. Going from port 3 to the LED and back to ground, it alters the time that the LED receives voltage in order to very rapidly blink the light and cause a change in the brightness. Objective 1, 50%. Using the same circuit by simply changing the value of the analog write into the pulse width modulation, we alter the brightness from 25% to 50%. Objective 1, 75%. In this objective, we've altered the number for the analog write pulse width modulation to 192, roughly 3/4 of the maximum pulse width modulation that we can input into our code. In Objective 4, we've increased the pulse width modulation to 255, resulting in a 100% duty cycle. And for Objective 1, the code is quite simple. It reads the percentage that we put in here. In this case, it's 25% of the total value of 225. So 225 divided by 4 is written to pin 3 in the form of the pulse width modulation, and that causes the LED to appear dimmer. Objective 2 requires no coding at all, simply having the power go in and through a potentiometer and the output of the potentiometer control the speed of a motor so that you can turn the motor off or you can turn it up very fast. It is a very touchy potentiometer, so the smallest adjustments will cause a change in the speed, but you can go slow or you can increase the speed to be very, very fast. Objective 3. In this objective, we use a potentiometer as an analog input to control the pulse width modulation that goes through a transistor to more accurately and safely control the speed of the DC motor. It also allows us a much more delicate adjustment to make the motor go much slower and then gradually speed it up and give us much more control over the speed of the motor. For Objective 3, the analog value of the potentiometer is read from analog pin 0 and stored into the pot value. That value is then printed to the serial monitor after the delay of 100 milliseconds. The potentiometer value is then scaled via the map function. Instead of being between 0 and 1023, it is scaled to be between 0 and 255, proportionate, and stored into the PWM output value integer. That integer is then analog written to output pin 3, which is a pulse width modulation pin that then controls the transistor that controls the motor. In Objective 4, we use a potentiometer and a push button to turn the motor on and off. Through the transistor, the motor is activated when the push button is pressed and when the value from the potentiometer is greater than 500. In this case, if I press the button while the potentiometer is turned down too low, it won't turn on. And if I don't press the button and turn the potentiometer up greater than 500, it also doesn't turn on. It isn't until it's above 500 and I press the button that the motor activates. After the delay of 100 milliseconds, the analog input from the potentiometer and the digital input from the push button are both read, and the potentiometer value is sent and read out in the serial monitor. If the push button is pressed and the potentiometer value is greater than 500, then pin 9 is written high. If either of those conditions are not met, the pin 9 output is set to low.